Hello, good afternoon. I thought I would just take you through a few of the improvements I've made to the BBC Micro emulator's cassette interface. I've been working on some improvements to that for about the past year, so I thought I'd just show a few of them off. This will probably be part one. There are some other things which I think will be better served by a separate video. Um, so what we have here is this one here on the left is an unpatched copy of BM, and the one on the right has my TOH1 RC7 patched. TOH is Tape Overhaul, so this is my patched version. If you just have a look at the tape menu, there's no tape loaded here, but you can see that catalog tape is a selectable option, even though there's nothing to catalog. Whereas if you look at the patched version, catalog tape is grayed out if there's no tape loaded, so that's just a sort of contextual UI improvement to start off with. If we load up a UEF file, if we load a UEF file in here, again, no change to this menu. I mean, you can catalog tape and it now shows something, but there's no way of knowing that just from the menu. Whereas in the patched version now, catalog tape is no longer grayed out, so you can see there's a tape loaded. And also eject tape, this brings the tape menu in line with the disk menu, but eject tape now names the tape image that you've got loaded. So there's just a couple of kind of contextual UI things there, which are basic improvements to start with. Okay. We have much improved UEF support than we had before. What we're going to do is we're going to use a tool from Quadbike called Tibet UEF, which, as the name suggests, is used to create UEF files from Tibet source files. But it allows you to specify various different chunk types to encode the data as various different chunk types. So we're gonna make a couple of UEFs here. The first one, we're going to use chunk hexadecimal 102, which is the explicit start, stop, and parity bits chunk type, where every framing bit within the serial stream is encoded explicitly within the UEF file. So we now have a 102.UEF. And the other chunk type we're going to use is 114. Now, this was never intended for storing data, but I've argued elsewhere, and you can read this in the Quadbike documentation if you're interested. I have argued in the past that chunk 114 is actually the only UEF chunk that provides complete generality, even though it was never actually intended for use storing data. So we'll have one of those as well. Now, if we start up an unpatched copy of the emulator, and a patched copy of the emulator. Okay, and we load up, we're going to load up, first of all, the chunk 102 UEF, start cataloging that. And then the chunk 102 in the patched version of the emulator. I'll just turn the speed up on those. And the unpatched version can't see data in chunk 102, whereas the patched version is now able to load that. So there's that. Also, chunk 114, we can take chunk 114 in both of these emulators now. And again, this is capable of loading from chunk 114, even though chunk 114 was never actually intended for use storing data, but it just happens, as I say, to be the only one that provides complete generality. So does now BM TOH does now allow loading from chunk 114 in UEF files. So that's nice. So that's an improvement. Now there are lots of other improvements to the UEF format. It recognizes many more chunk types. Even if it doesn't necessarily do anything with them, but that's the sort of most notable thing, is that it now supports loading data from those two chunk types. Right, saving to tape. This is something that previously you could only do using BBEM for Windows, which is fine unless you're not using Windows, in which case that was kind of a problem. So we have a disk loaded here. We're going to load this array file off the disk. and then select the cassette interface, and then we're going to save this out to the tape. But before we can do that, we need to enable record mode. If you don't switch this on, then nothing's going to actually appear on the tape, so it's important to remember to do that. If you're doing this and it's not working, it's probably because you've not switched that on. So we're going to save that out to tape now, and we'll just speed this process up so it's a bit faster. Okay, so if we look at the tape catalog now, you can see that we've saved that out now, and you can of course obviously save a copy out to tape. There are 4 file formats. If you're starting with a blank tape, you can just save it as, you can pick any of those formats. So we're going to save out, say, we're going to save out a UEF here, a.UEF, and if we run this again now, and we load that UEF file we just saved, and we can catalog the tape there, and we should see the file that we saved. So that's nice. Saving to tape, there you go. Continuing with the saving to tape idea, what we have here now is that we have a disk loaded, so we're going to load a file off the disk. And we also have a tape loaded. If we have a look at the tape catalog, you can see there's already a copy of this array on the tape. So going to enable record mode, and we are going to select the cassette interface and save this to the tape. And what that should do is append to the append after the file the array file that's already on the tape. So if we look at the tape catalog, there it is, array and B, and we could now save that out and you know, load it back in again and prove that it's possible to persist it, but that works. You probably want to get on with things. Okay, the Tibet file format. Now, if we start up a patched copy here. Now, there's a new file format which I came up with for the quad bike. It's mainly so I could debug problems with quad bike. It was helpful to have a file format that was really easy to inspect sort of what was going on. So what we're going to do is at 1200 baud, we're just going to save a blank basic file out to the tape. Nice and simple. So there it is at 1200 baud. And then we're going to switch to 300 baud, and we're going to do the same thing again. I'll just speed that up. Okay, and then we're going to save this to disk as a Tibet file. Now, because a Tibet file is just a text file, and that's the major advantage of it, we're going to put a TXT extension on the end of this. You wouldn't normally do this, but we're going to put a TXT extension on there just so that we can see the file. So this is a Tibet file. Very quickly, there's a version line. Silence is measured in seconds. There's 0.9 seconds of silence. There are some hints which start with a slash, which means the decoder is free to ignore them. So these are, you know, advisory. You've got leader. This is measured in number of 2400 hertz cycles. So that's an integer number of cycles there. Then we have data sections, which contain actual data. Now, the way this is formatted is that each line is 20 characters long. And at 1200 baud, that's convenient because it means that each line is exactly one data frame. Each one of these individual characters, the dots and the dashes, represents 1/2400th of a second of tone. So 2 together at 1200 baud, 2 together is 1 bit. So each of these pairs of characters is a single bit, and each line is a single frame. So each one of these lines will be seen by the operating system as a byte of data. If we go down to the bit that we saved at 300 baud, now the formatting, the 20 characters per line thing isn't quite so convenient here because each line is no longer a data frame. But if we delete some of the white space, and you can do this because it doesn't care about white space within data sections, so you can format the lines however you want. But we can see that each bit is now 8 characters long, so 8/2400ths of a second. So they're 4 times longer than they were in the 1200 baud section. So that's what 300 baud looks like in Tibet file. And that's quite a good demonstration of the Tibet file, advantages of the Tibet file, because you can just inspect things like this. You can just look at it. They're easy to edit with scripts, manipulate with scripts. You can write them using, you know, you can automate the writing of them. They're easy to edit, easy to inspect. You can see what's going on. So I quite like them. And BM now supports loading and saving them, and also a compressed version, which is called Tibets, which is just gzip. Yeah, so that's the Tibet format. There's one other thing we're just going to look at here. Notice that in the 1200 baud file, there is no duplicate data CRC byte at the end of the block. Now, we discovered that the operating system 1.2 sends out 2 bytes of duplicated data CRC after the end of each block. But because of the length of the output pipeline, the write pipeline, transmit pipeline in the ACIA, those 2 duplicated data CRC bytes never actually make it out to the tape because the ACIA is reset before they can actually make it out of the pipeline. So now a naive saving to tape implementation might have those, or would send forward those duplicated data CRC bytes onto the tape, but they're not here because this does accurately model the length of that output pipeline, and the bytes are destroyed when the ACIA is reset, so there's no duplicated byte at the end of the block there. I just wanted to show you that because that's going to become important in a second when we look at operating system 0.1. If we load the 0.1 OS ROM, now the OS 0.1 ROM actually does leak 1 duplicated byte of data CRC, and we've observed this happening on real-world tapes. So you can tell which tapes were mastered using OS 0.1 because you can see this duplicated data CRC byte. And as I say, this can be seen on real tapes. So if we now save this out as a Tibet file, tibet.txt, don't need that anymore. Number 7. There it is. You can see it clear as day. There are 2. There's a duplicated byte of data CRC at the end of the block, and that's because we saved it out on OS 0.1. So that output pipelining behavior is correct for both operating systems, which is quite nice. This is what you would see coming out of an actual Beeb with an OS 0.1 ROM in it, so that's quite cool. One final thing for part 1 of this video is the mischief menu. I just need my original operating system back. There we go. If we start cataloging the tape we've got loaded here, you will notice tape menu. There is this new mischief thing, which is a menu for developers. Basically, it was quite useful. I introduced this because I was debugging the unit tests, and it was useful to be able to introduce tape errors. So you can corrupt ACIA reads, change the value. I think it just inverts every bit is how I implemented that. You can generate framing errors and parity errors coming out of the ACIA. Now, the operating system actually doesn't care about framing errors. It doesn't check for them. So you can click on that to your heart's content and nothing will happen. Nor does it care about parity errors. Doesn't care about those either. Click on that, nothing happens. But it does care about its precious block checksum, the CFS block checksum. So if you corrupt a byte of data, that's obviously good enough to corrupt the CFS checksum. So if I click on that, that will now generate an error, hopefully. Unless I got it. No, there we go. Yep, that worked. So yeah, there's an error. So I think that'll do it for part 1 of the video. That's just some of the things. I'm going to look at the tape noise generation and also the Hoglet histogram, the TDRE bit data register writes to TDRE bit change timings. But that's probably best done on hardware, so that'll take a separate video. So there we go. Thank you for watching. There's some improvements that I've made to BM's cassette support. Thank you.